Okay, thank you. We'll try this again. So we've already had two talks about MRIs. It was the main focus of the last Astro-GR meeting, and now asked to give a bit of an overview on the data analysis and relativity side of things. So we'll be talking about that and also some of the science applications we hope to use these observations of MRIs. I'm going to begin by talking a bit about the properties of MRI gravitational waveforms. I'll then talk about estimates of the likely number of MRI events we'll see with LISA, and then talk about some of the science applications. We can use MRIs as probes of black holes in the comparatively local universe, possibly as a probe of cosmology, and also to test aspects of relativity theory. And then, depending how much time I have left, I'll talk a bit about detection of MRIs, and also modelling of the gravitational waveforms. So as we've heard in the talks by Tal and Mark earlier in the conference, an extreme mass ratio in spiral is the spiral of a compact object into a black hole. We know that the centres of most galaxies contain supermassive black holes, and these are typically surrounded by clusters of stars. Now these stars will interact with one another gravitationally, and over time they can diffuse onto orbits that pass very close to the central black hole. If this happens, as the star swings past the central black hole, it will lose energy and momentum in a burst of gravitational radiation, and if it passes close enough, this can leave it bound to the central black hole, and then over a period of 1 million years or so, it will gradually in-spiral via gravitational wave emission, and eventually plunge into the central black hole. So extreme mass ratio in-spiral is the in-spiral of a compact object, either a white dwarf, a neutron star, or a black hole, into a supermassive black hole in the centre of the galaxy. Now, what makes these sources particularly interesting is the in-spiral is comparatively slow because of the extreme mass ratio. And so we could observe these sources with LISA for as many as 100,000 waveform cycles over the last 3 to 5 years of the in-spiral prior to the plunge. The other thing that's nice is the system, we believe, will be comparatively clean. This small object, therefore, essentially acts like a test particle, and it probes the structure of the space-time outside the central object. Now, the gravitational radiation during these last 3 to 5 years is all emitted when the particle is in the strong field region of space-time. We expect in the standard scenario that the orbits will be both inclined to the equatorial plane of black hole and eccentric. And over 3 to 5 years, the object will in-spiral, and so it explores a great deal of the region close to the central black hole. Now, at any moment, the object will be on a nearly GD6 orbit around the central black hole, and this is characterized by 3 fundamental frequencies, and the emitted gravitational waves will contain harmonics of these 3 fundamental frequencies. So the frequencies are the orbital frequency, i.e. 1 over the time between successive periapse passages, and then we also have the perihelion precession frequency, and also the frequency of precession of the orbital plane that arises due to the spin of the particle. Now, we often refer to MRI orbits as zoom and whirl, but this is mainly because of the extreme perihelion precession you can see in these systems. I've got a sequence of movies that illustrate this. Each of these, the top left-hand panel shows the radial gravitational potential that the particle is moving in. The top right shows the projection of the orbit in the equatorial plane of the system, and the bottom 2 panels show the gravitational waveforms, the plus and cross polarization. So this is a system orbiting a Schwarzschild black hole at a periapse of about 500 m, and we see the orbit's very simple. It's almost an ellipse, although there is a slight amount of perihelion precession, even this far away. If you go a bit closer, the perihelion precession becomes more pronounced, the orbit advances fairly significantly, but even here we still have a periapse of around 50 m. Now, the gravitational waves have a characteristic structure that you see sort of higher frequency and higher amplitude bursts when the particle is closer to the centre, interspersed by lower amplitude and lower frequency radiation when the particle is further away. Now, this can become very extreme if you get very close to plunge. Now, this is an example. Again, this is now curve, but if the orbit is very close to plunge and the particle can come very close to the inner maximum of the effective potential, it can whirl round the central black hole many times before going back out to apex. Now, this is a particularly extreme case where we're likely to see anything like this in practice. But in principle, you can whirl around the central black hole several times before going into apoapsis. So that's what we mean by zoom and whirl. We see the particle zooms out to apoapsis, then comes into periapsis, whirls around the black hole several times before zooming back out again. And the gravitational waves reflect this waveform structure. Things are even more interesting for generic orbits that occur. In this case, I'm now only showing one waveform polarization, and we're seeing the orbit projected in the equatorial plane and projected viewed from the side. If you have a generic inclined and eccentric orbit, the orbit fills up quite a lot of the space around the black hole, but the sort of underlying waveform structure is quite similar. You see bursts of high frequency radiation near periapsis, interspersed by lower frequency radiation emitted on the zoom to apoapsis. But the whole waveform pattern is modulated as a consequence of the orbital plane position. Now, all this complexity encodes a great deal of information about the system, and that's what we want to extract and use for science. So I'm going to talk now about this EMRI event rate. There are three ingredients that go into estimating the rate. First of these is the intrinsic rate at which a black hole will eat compact objects. Now, as Tal and Mark explained, there's a lot of detailed physics that goes into these rates, and so they're actually not known particularly well at the moment, but hopefully these will give us some constraints on that. We also need to know the number of black holes that LISA, or potential LISA sources, the number of black holes in the mass range from 1 × 10⁵ to 1 × 10⁷ solar masses, which we might potentially detect with LISA. And then we need to know about the detector. We need to know what signal-to-noise ratio we need in order to be able to confidently say that a signal is a true signal and not just an artifact of the noise. And we also need to know how that signal-to-noise ratio depends on the system parameters. So, as Tal was explaining, the intrinsic rates are rather uncertain. So this first numbers I'm going to give you, I'm assuming a very high rate of 10⁻⁶ inspirals per year. That's definitely the upper end of possible range of event rates we're likely to see, but it gives you an idea of typical numbers. And I'm going to scale this to other galaxies using a power law of m⁵. Now, this is based on assuming all stars in the black hole were created at the same time, one Hubble time ago, and then it just evolves as a result of dynamical friction. Mark Freitag has done some more detailed calculations recently, and he thinks that the rate actually might scale more like m⁻⁻². And so we could actually expect to see more inspirals in lower mass black holes than larger high mass black holes. To estimate the number of black holes in LISA sensitivity range, what you can do is take a measured galaxy luminosity function and combine that with the correlation between galaxy luminosity and velocity dispersion, and the n-sigma relation, which relates black hole mass to velocity dispersion. And if you do that, you find that in LISA's sensitivity range from 10⁵ to 10⁷, the mass distribution is roughly flat in log n. So in dm, m is roughly constant at about 1 black hole per 1,000 cubic megaparsecs. For the LISA part, we can actually do things a bit more accurately than we can on the astrophysical side. But to estimate the signal-to-noise ratio for detection, we need to understand how we're going to do the data analysis. Now, if I get onto that later in the talk, I'll explain our current level of understanding about that. But the very first estimate we did was for one particular type of search, which we call a semi-coherent search. We need a signal-to-noise ratio of about 30 or 35 to pull the detection event out of the noise. Okay, so with that threshold in mind, you can compute the signal-to-noise ratio over the last 5 years of inspiral and work out how far away we can see typical systems. I won't go into the details, but the way we actually computed signal-to-noise ratios in practice were to use a particular family of approximate EMR waveforms, which we call numerical kludge waveforms, and we combine these with something called the synthetic LISA, which is a simulator that mimics the LISA response, and allowed us to compute signal-to-noise ratios of typical events. And we did this under two sets of assumptions, which I call pessimistic and optimistic, but these are optimistic and pessimistic about the detector, and don't fold in any of the astrophysical uncertainties, which are potentially much bigger. The optimistic situation, we assumed that LISA lasted for 5 years, and that for all of that time, LISA was fully operational. So if LISA is working as planned, you can synthesize two Michelson responses using the three arms, and this combination gives you the optimal signal-to-noise ratio of these TDI variables A, E, and T. If we also assume that you could get rid of the galactic white dwarfs, which create this foreground noise, to the maximum level you predict is possible from information theory, and we also make assumption about the algorithm that we could actually do it as using 3-week coherent segments. I'll explain what that means later on. Pessimistic assumptions, we assumed the mission was only 3 years and that there was a failure on one of the satellites, so that we could actually only construct one of these synthetic Michelsons and hence not get the full signal-to-noise ratio. We assumed that we could only subtract white dwarfs down to the best level that was then possible. Now we've actually already done better than that now, so that's something we don't have to make. And we assumed we weren't able to use as long initial segments in our search as we could. And putting all this together and dividing things up into mass classes for the central black hole and the cosmic object, we got rates that look something like this. So what you can take away is that our dominant sources are in spirals of 10 solar mass black holes into million solar mass black holes, and if we were really optimistic, we might see several thousand events. If we're more realistic, we're talking about several hundred, but then if we fold some of the astrophysical uncertainties in, we're down to perhaps a few tens or maybe 100 events. I'm going to spend a bit longer talking about the distribution of event parameters, just to give you some idea of what we might see. For those initial estimates, which we did about 4 years ago, we didn't actually treat many things as well as we could have. For instance, we made no account of the fact that an event which is closer can actually be seen for much longer. Knowing the signal-to-noise ratio of a system is 35 in its last 5 years, you actually have no chance of detecting that system because you need LISA to turn on precisely the moment that it entered that last 5 years before plunge in order to pull it out. Whereas a system that's closer, if you turn LISA on 15 years before plunge, you might still get enough signal-to-noise ratio over the time from 15 to 10 years before plunge to actually pull the system out of the noise. So what I'm plotting on this graph is curves of constant detectable lifetime, which means you can actually see a source for LISA could turn on any time within a 1 year phase of the in-spiral, and you could still get enough signal-to-noise ratio for a detection. And you don't need to understand that in detail, but just that these curves indicate the volume of the universe to which we're likely to be able to see EMRI events. So I'm plotting mass on the horizontal axis and redshift increasing downwards on the vertical axis. Each of these curves is for a different value of the spin. The red curve is for nearly extremal, green is 0.99, then 0.9, 0.8, 0.5, 0.2. The black curve here is 0, and then the inner curves are actually for retrograde in spirals into black holes of spin 0.5 and 0.9. So if we have nearly extremal black holes and prograde in spirals, we can see these out to redshift of 2. For more modest spins, we're talking about redshifts of 1.5, and retrograde in spirals, we can only see out to redshift of about half or so. But we're most sensitive to black holes in the mass range from about 7 times 10 to the 5 up to 3 times 10 to the 6. These new curves are taken from, well, it's a bit confused, but these come from a simulation by Marta Terry, and they approximately track black hole evolution tracks. So the only point of putting these on is that things that we're probing with LISA end up as black holes between 1 and 5 times 10 to the 6 solar masses today. Now if we integrate over mass, we can convert this into a number distribution with redshift. And for this plot, I'm actually assuming not a 10 to the minus 6 inspirals per year is the intrinsic rate for the Milky Way, but 10 to the minus 7. The red curve is assuming that well, for both of these plots, I'm assuming that we only have inspirals of 10 solar mass black holes into supermassive black holes. The red curve is assuming all black holes have a spin of 0.9. The green curve assumes all black holes are non-spinning, so reality will be somewhere between the two. Now, with a Milky Way rate of 10 to the minus 7, you predict of the order of 150 events if all black holes have a spin of 0.9, or about 60 events if all black holes are non-spinning. But the distribution in redshift is quite broad, it's peaked around a redshift of 0.5. Now these vertical lines indicate the maximum redshift we're likely to see. So you can integrate the tail of this distribution and find the point at which you expect there to be exactly one source at higher redshift than that. Now for a rate in the Milky Way of 10 to the minus 7 inspirals per year, you predict this maximum redshift to be about 1.35. If the rate was a factor of 10 lower, 10 to the minus 8 per year, the maximum redshift event we're likely to see will be around 1.15, and if the event rate was 10 times higher, we'd be pushing out to a redshift of 1.45. If we divide those 150 events up into different mass classes, I haven't covered all masses here, but I'm 3 intervals which are equal in log m. The red curve is the lowest mass between 2 times 10 to the 5 and 5.5 times 10 to the 5. The green is the between 5 times 10 to the 5 and 2 times 10 to the 6, and then the blue is 2 to 5 times 10 to the 6. So we see more events in this middle mass range around 1 billion solar masses, but we also see a fair number that are heavier and a fair number that are somewhat lighter. You can do the same trick now, assuming that events are not black holes, but they're white dwarfs or neutron stars. Now, and this is what you end up with. Now, for these curves, I'm actually assuming that the rate of neutron stars in spirals, the rate of white dwarf in spirals, the rate of black hole in spirals are all the same at 10 to the minus 7 per year. So at those rates, you'd see 150 black holes distributed between up to redshift of 1.2 or so. Neutron stars you see of the order of 15, peaked at redshift of 0.2, and not really anywhere above 0.4, and you see about 3 white dwarf events peaked around redshift of 0.1. Now, if the white dwarf inspiral rate was intrinsically a factor of 50 times bigger than the black hole inspiral rate, which it could be, you then see as many white dwarf inspirals as you would see black hole inspirals. So, if we do see all of these events, we want to know what science we can actually do with them. Now, from Fisher matrix predictions, you can work out the accuracy with which an MRI observation can determine the various parameters of the system. Now, these events are much lower signal noise ratio than the supermassive black hole in spirals, but they also, you get many more waveform cycles. So that actually allows you to do comparatively well in determining parameters. We think, and this has been recently confirmed using Monte Carlo type simulations, that you should be able to measure the mass and spin of the central black hole and also the mass of the small body to around part 10 to the 4. You don't get quite such accuracy on sky position or distance. Sky position we're confining to maybe a square degree, and distance possibly to 3 to 5%. What you can do is, since you'll be seeing these events at a redshift of 1.5 or so, you can use these EMR events as a probe of the supermassive black hole mass and spin functions in the comparatively low redshift universe. So one example of this, the mass function I was using to produce those event rate estimates in the previous slides was this one that's based on taking the galaxy luminosity function, combining it with L sigma and M sigma relations, and you end up with this sort of purple curve here. So black hole mass on the horizontal axis, and black hole number density on the vertical axis. Now you can also measure velocity dispersion directly using a Sloan digital sky survey, and if you do that, you get this red curve, which in the range where LISA is sensitive is 1 to 2 orders of magnitude lower. Now, the SDSS derived results are not entirely accurate in this regime because we're getting to the level of the where the velocity dispersion is comparable to the sensitivity of the detector. But there are these sort of two alternative predictions of the mass function in that range. Now, if the SDSS or Chef mass function was correct, then not only would you get less events, but you'd actually find there'd be a different mass distribution. This is one possible prediction for the distribution of masses. If the Chef mass function was correct, you'd be peaked at higher masses, around 2.5 million solar masses, whereas if the Aller and Ridgestone one based on the luminosity function is correct, you'd be more like 1 million solar masses. So these two extreme mass functions could be distinguished with as few as 10 events, but we'd like to know how many events we need to say a bit more. We also will be probing galactic nuclei. Now, one of the things we will definitely learn is something about the dominant EMRI formation channels. In the standard picture that I described first, where things are captured on these nearly radial orbits with very large apaps, then the orbit is expected to be both inclined and eccentric when it enters the LISA band. But there are alternative mechanisms. One of these is the binary tidal splitting that Tal mentioned, and in that case the star is captured in a much larger periaps, and this means that by the time it is radiating continuously in the LISA band, it will have circularized. Although, since there's no preferred direction for this mechanism, it will also be inclined to the equatorial plane. But another possible formation channel is formation of stars in a disk, and if you had formation in an equatorial disk, you'd expect the inspiraling objects to be not only circular, but also equatorial, and so you can distinguish the relative importance of these three channels by considering the number of inclined eccentric orbits you see versus the number of circular inclined versus the number of circular equatorial. We'll also learn something about the relative numbers of black hole, neutron star, and white dwarf inspirals. Now, exactly what this tells us is not really entirely clear, because the efficiency of mass segregation will determine how many black holes sink to the center versus how many neutron stars and how many white dwarfs, but we can't necessarily disentangle that from the stellar mass function, which determines the number of black holes there are in the cluster in the first place. But the other thing we might learn is if we did see the inspiral of 100 or 1,000 solar mass object into a supermassive black hole, then that would be verification of the existence of intermediate mass black holes. We can also potentially do cosmology with the EMRIs. As various other people have discussed already, gravitational wave signals will give you the luminosity distance absolutely in a way that's not tied to the local distance scale. So if you were to observe a single extreme mass ratio inspiral event with an electromagnetic counterpart so that you could measure the redshift independently of the luminosity distance, then you'd actually be able to measure the Hubble constant basically to the same accuracy as you're measuring the luminosity distance, which is 3 to 5%. And if you had n of these events, this would go down like 3 over the square root of n. Now, what was worked out recently, which is potentially quite interesting, is that even if you don't have electromagnetic counterparts to EMRI events, which we don't have reliable mechanisms that would give these, you can actually still use an EMRI observation to estimate the Hubble constant in a statistical sense. So the idea is that you see a LISA observation, and this gives you a certain error box in on the sky, both sky position and distance, in which that source could be. Now you then go and look with a telescope at all the galaxies that you can see in that particular error box, and for each one of them you let it have a vote on what it thinks the Hubble constant would be if it was the host of the MRI. Now you can actually, we have real data from Sloan. This is something I stole from McLeod and Hogan's paper, but these boxes are typical sizes for the MRI error boxes. The upper panel and lower panel differ only in the redshift at which they've placed the source. They extrapolate the Sloan catalogue out to higher redshift. Now, you could have as many as 1,000 galaxies in at least an error box, but each one of these galaxies has a particular redshift, and you then allow it to say, well, let's say I was the host of the EMRI, then I would say the Hubble constant had this particular value. Now if you do this, you end up with a distribution of possible values of the Hubble constant, which looks something like this. And for this simulation, they assume the Hubble constant was actually 70 kilometers per second per megaparsec, and you see that the recovered distributions are centered very close to this true value. And so you find that doing this statistical estimate of the Hubble constant, if you had about 20 EMRI events at a redshift less than a half, which is quite reasonable, we should be able to determine the Hubble constant to an accuracy of about 1% or thereabouts. And this is already doing the survey of galaxies in the least error box is already technologically feasible. So the third area of EMRI science that I'm going to talk about is testing the black hole hypothesis, i.e. the assumption that we make that the massive compact objects we observe in the centers of most galaxies are indeed spinning black holes, which are described by the Kerr metric of relativity. Now, the extreme mass ratio systems are good systems for doing this kind of tests because the inspiral object acts like a test particle in the background geometry of the central black hole. So you can use the emitted gravitational waves to, in some sense, map out the space-time structure around the central object. We call this orthorodicity, from the Greek word orthros, meaning in ancient Greek sacrificial pit. Apparently in modern Greek it means something less pleasant, and so our Greek compatriots prefer to use the word oleodicity instead. Now, what could possibly cause a system in the universe to not be a Kerr black hole? Well, there are several possible reasons. One of these is that there is some complicated astrophysical explanation. There is matter exterior to the black hole, which, either by accretion or by creating a tidal field, influences the orbit. I'm not going to talk about that much because I believe Enrico Baruzzi is going to be talking about that this afternoon. But deviations can also arise if the object was still, relativity was still the correct theory of gravity, but the central object was not a Kerr black hole, but something more exotic, boson star or a naked singularity. And deviation can also arise if general relativity is not the correct theory of gravity. Okay. So the second of those options, well, we know that any vacuum axisymmetric spacetime within the context of general relativity can be characterized by its multiple moments. Now, for a Kerr black hole, you satisfy the no-hair theorem. Now, what this really means is that we have uniqueness theorems for in the context of relativity, which tell us that if certain assumptions are satisfied, the spacetime must be described by the Kerr metric. The Kerr metric has only two free parameters, the mass and the spin, and all the other multiple moments are therefore determined. So a Kerr black hole has no hair because all of the multiple moments, the higher multiple moments, n, l, and these are the mass moments, and SL, the current moments, are determined by the mass and spin of the central black hole via this relation. But if either of those assumptions that go into the uniqueness theorem are violated, then we would expect to see deviations in these multiples. Now these multiples are actually encoded in things we can observe with gravitational waves, specifically the precession frequency, perihelion precession and the orbital plane precession, but also the inspiral rate, or the number of cycles that the object spends near a certain orbital frequency during the course of the inspiral. And in fact, it was demonstrated by Flint and Ryan in 1995 that if you do an expansion of, in this case it's the perihelion precession frequency, as a function of the orbital frequency, you find that the different multiples in space-time enter this expansion at different orders. So the lowest order gives you the mass, the next order gives you the spin, the next order gives you the mass quadrupole moment, and so on. And so in principle, if you observe the change of precession during the course of an inspiral, you can map out this function and pull out the moments one at a time. Now the problem with this kind of approach is that you're trying to expand your space-time as a function of these multiples, and we know that the curved space-time has an infinite number of them, so it's hard to reproduce a curve limit. So various authors have looked at what Babak and Lampadakis call quasi-Kerr space-times, which are space-times, solutions of, within the context of relativity that can be dialed arbitrarily close to Kerr by setting a small parameter close to 0. So this is look at Collins and Hughes, Babak and Lampadakis, also Brock and Cutler, and myself. So if you look at these quasi-Kerr spacetimes, you can do a Fisher matrix. This is just an example of how the precession rate in one of these systems might look like. These different curves correspond. This Q is the potentially small parameter, Q equals 0, which is this black line, is the precession rate for Kerr, and these other lines show what happens when you change this small parameter. So you find that for one sign of deviation, the precession rate behaves qualitatively in the same way, although it does change, whereas if you change this small parameter in the opposite sense, you actually get a very different behavior. So this will be observable. If you do a more accurate analysis using a Fisher matrix for a waveform template that includes a quadrupole moment parameter as well as mass and spin and all the other things, you find that you should be able to measure the quadrupole moment of the system to an accuracy of about 0.1%, while you're simultaneously measuring the mass and spin of the system to the same accuracy. So this is then a strong test of the no-hair property, because if you measure these three things independently, you can check that they are consistent with the prediction of the no-hair relation. To put this in context, boson stars typically will have mass moments that are mass quadrupole moments that are about 10 to 100 times bigger than Kerr. So this is easily enough to distinguish those. This was all kind of based on weak field analysis. In the strong field, things could be even more extreme. One particular example is that you can actually see chaotic motion. So these are Poincare maps. They show the radial velocity as a function of radius every time a particle on a particular orbit crosses the equatorial plane. If you have a third integral of motion, as you do in Kerr, you see these nice closed curves, but if the third integral is lost, you can actually see something more stochastic. Now, if this did exist in nature, you might be able to detect this using a time frequency analysis. The frequency decomposition of a regular orbit has well-defined peaks, which are low integer multiples of the three fundamental frequencies. But if you have something that's chaotic, you just see essentially noise. Now, this can exist in some of these spacetimes, these quasi-Kerr spacetimes, but it's unlikely to be astrophysically relevant because you have to tune your parameters quite carefully in order to get them. So in practice, even if spacetimes are not described by the Kerr metric, it's more likely that the small deviations in the precession rates will tell us that rather than these more sort of significant differences. Okay, so I'm running out of time, but I'll talk very quickly about the sort of third thing that could cause deviations from relativity, and that's a failure in the theory itself. So all of this research that has worked on precession rates in quasi-curved spacetimes has been focused on spacetime mapping. It's been focused on looking at the metric outside the central object and finding whether or not it's consistent with Kerr. But this is not really a test of relativity because it's reasonably well known that in several alternative theories the Kerr metric is also a solution. There was a recent paper by Soltis et al. In which they considered several alternative theories. They considered some F-bar theories, Martini gravity, and what they call generalized quadratic gravity, in which the field equations look something like this. There's K and L are functions of the Ricci tensor. But basically, if you have an alternative theory in which the vacuum field equations depend only on the Ricci tensor and the Ricci scalar, then since these both vanish for the Kerr metric, it will also be a solution in those theories. Now, what Soltis et al. Didn't really talk about was the fact that if you change the field equations, even if the static solution could be the same, the dynamical solution is not going to be, and so you will be able to see differences due to the change in the shape of the gravitational waveform, but also in the rate of energy loss and angular momentum loss from the system. So, how might we do space-time mapping in practice? This is a cartoon of one way it might be done. It's hard, so I'd say the first thing we should do is assume that relativity is correct, that we've got a vacuum space-time, and that it's axisymmetric. If we do that, we already know how to extract multibell moments from our observations. Now, once we've got the multibell moments, that basically tells us the metric. If we're assuming the relativity is correct, we have both the metric and the field equations, and we can check that those are consistent with the gravitational waveform we're observing, and also the rate of energy loss from the system. If they are consistent, you can do sort of various things. You can check that the multibell moments satisfy the no-hair property. You can see whether the emission cuts off at the right point, i.e. the last stable orbit is in the right place. And you can also quantify the tidal interaction. So, as well as gravitational waves going to infinity, you actually lose some energy and momentum into the central object. Now, for a Kerr black hole, you know what proportion of the energy should be lost that way. But if the central object is something else, this tidal interaction, the energy loss going into the central object, would be a bit different. And you can pull that out from the observed gravitational wave field, you know how much energy is going to infinity, and from the rate of in-spiral, you know how much energy is being lost from the system, and the difference between those tells you how much is going into the tidal interaction. Okay, so this is probably the most likely sequence we'll see in practice, but in principle we can get to this stage and find that we've got a set of multibell moments and gravitational wave that are inconsistent with the dynamical theory. And so we then have to go back and relax all of these assumptions, and the first one to relax would be the fact that the space-time is a vacuum. So if you then assume the relativity is correct, the space-time isn't a vacuum, but it is axisymmetric, then in principle we hope to be able to extract both the metric and the matter energy momentum tensor from the observations. Now we don't really know how to do that as yet, but we hope it might be possible. If you can do that, then once again you get to the stage where you can check for consistency with the dynamical theory, and then if it is consistent, you can test various things, including whether the strong, weak, and dominant energy conditions are satisfied by the material in the system. But if it's not consistent, then at that point you need to start modifying GR and considering whether any alternative theories are more consistent with what you're observing. And then depending on what you see, you may make various conclusions about what the central object is. It could be a Kerr black hole, it could be some kind of exotic object with a Kerr exterior, it could be a big black hole, it could be a native singularity, and so on. Okay, so I think I'm now out of time, so I will not, after all, talk about data analysis, but I'll just skip to my summary slide. The fact is that we believe we know how to do MRI data analysis, and we also know how to model the sources. Oops. I went too far. So, in summary, Lisa, hopefully you could see as many as 1,000 MRI events. It's very dependent on the astrophysical rate. It could be 10, it could be 100. The signals are very rich, they tell us a lot of information about the system, and we can use this to do science, probe black holes and molecular nuclei, we can do cosmology, and we can also test the theory of relativity in the strong field. There are various data analysis algorithms that are being developed, and they are showing promising results in the context of the LISA mock data challenges, so it looks like hopefully we'll be ready by the time LISA flies in 2018. I'll finish by plugging the same paper that Mark Freitag plugged, which was the review paper that came out of the last LISA Astro-GR meeting, which goes into all these issues in more detail. Thank you.